Okay, today we're going to talk about gravity. More in particular, we're going to talk about the acceleration due to gravity. Um, the acceleration due to gravity is given a symbol because we use it so often. We give it a symbol g. Again, often in textbooks you'll see this written as 9.8 meters per second squared. Instead of this number, we're actually just going to round this off to 10. It just makes it very convenient to work with. Again, this is an average because the world isn't a perfect sphere, and we take an average all over the world, and we get about 9.8, which we're just going to consider it to be about 10. Well, what does this exactly mean, and how does it look? The only thing I want to make clear today is that when you do throw an object into the air, this always acts. In other words, it doesn't take a break. Often people are confused and have the assumption here that if I take an object and throw it into the air, and it goes all the way up to the top and then falls back down, gravity will take a break somewhere along its path. Generally, people will think that at the top of the path right here, gravity is zero. That's of course a big misconception. Gravity doesn't take a break. It's always 10 meters per second squared down or towards the center of the Earth. Okay, so gravity isn't taking a break at the top. It's always this number, around 10 meters per second squared. Just to give you an example here of how to use this, if I'll just take a cliff here, or a building, and if I have an object and I just drop it, so I'm going to make VI equal to 0. So here's this object here, this little ball, okay, and we drop it, and it's going to fall down this cliff of some height. Okay, this cliff has some sort of height. When this object falls, it has a VI equal to 0 and a height h. Well, suppose I want to know, how fast it's moving after a certain amount of time. Okay. Well, in order to do that, if we were given a certain amount of time, let's call it time t. If we're given that, we could use an equation here that says that d is equal to VIT plus a half AT squared. Now this won't tell me how fast it's moving, but it will tell me how far it's fallen. Of course, this will be 0. So I end up getting this. What I want to point out here, just with regards to gravity, is this guy right here, this squared term. If you notice, half of a will always be a constant. It'll be half of 10, which is 5. But because it's t squared, it means that if I let an object fall for 1 meter, or pardon me, 1 second, okay, 1 second after starting at 0, if I let an object fall for 1 second, it'll be moving at, I guess it would be half a, or 5 meters per second here. Okay, so I'll just make a chart here and just say that here's time and here's the height, or how far it's fallen. Okay, after 1 second, in this case, it would be around 5 meters per second. What about after 2? Well, after 2 seconds, because it's squared, you're going to get t squared, so that's going to be 4 times 5, which is actually going to be 20. And after 3 seconds, you're going to get 9, and 9 times 5 is 45. What I want to point out here is that the distance, okay, that this object is falling keeps increasing. Okay, keeps increasing. In other words, it started off in the first second only falling 5 meters. In the second, it fell an additional 15. In the third, 25. And you get the picture here. It can keep on going here. But 5, 15, 25, it's increasing the distance. And the reason that's happening is because it's increasing in speed. It is accelerating. Okay? A big misconception is that if an object falls, it'll go at a constant rate. Of course, this doesn't happen. It doesn't move at a constant rate. Instead, what it does is as that object falls, it goes here, here, and keeps getting longer in between successive seconds here. So it'll actually be increasing in speed. It'll be accelerating. Okay, I just want to point that out here, that it isn't linear because of this squared factor there.